Good afternoon and welcome to this presentation on computational modelling of the impact of salt marsh management interventions on coastal flooding. My name is William Bennet and I carried out this work as part of a team of researchers at Swansea University for the interdisciplinary CoastWeb project. Firstly, for those of you who might be unfamiliar with salt marshes, they are a coastal wetland that becomes inundated with the tide. They are a form of habitat home to a variety of specialised plants and animal species and are distributed widely around the UK as well as around Europe, as you can see in the figure. In addition, they are used extensively for grazing of livestock to provide a source of premium quality meat. As well as these ecosystem services, salt marshes are known to attenuate wave action. As such, they play an important role in coastal defence function. This project focused on the salt marshes of Wales in particular, and as such the TAF Estuary in southwest Wales was chosen, highlighted here by the green arrow. The TAF represents a typical Welsh estuary in terms of size, tidal characteristics and morphodynamics. It is a small macro-tidal estuary with a mean spring tidal range of 7.5 metres, a neap tidal range of 3.7 metres, and the River Taff has an average daily freshwater discharge of 7 cubic metres per second, with an extreme high of 60 cubic metres per second during winter and low of 0.6 cubic metres per second during summer. Because of this low freshwater influx and a large tidal range, at low tide the estuary consists of intertidal flat with salt marshes and mudflats intertwined by shallow drainage channels. Swell wave penetration into the estuary is limited by the orientation of the estuary mouth. Swell waves tend to come from the southwesterly direction from the Atlantic. However, locally generated wind waves within the estuary can be significant and have a wider array of directions. In total, the salt marshes occupy a total area of 2.79 square kilometres and are characterised by the woody perennial Atriplex portulacoides, which dominates much of the marsh. The historic village of Larne, located at the fringe of one of the largest marshes of the estuary and regularly floods during winter storms, attracts the attention of policymakers and coastal managers, as there is an urgent need to implement a sustainable solution to protect the village. The current management policy in the TAF estuary is to allow natural development of undefended shores and reduce the risk of flooding and erosion. This creates a number of differing policies depending on the assets at risk and the time frame considered. The modelling approach made use of the open source Delft 3D numerical modelling suite. It was chosen for a variety of reasons. Delft 3D is process based and includes functionality to model a wide array of scenarios in time and space. In particular, it allows for modelling the interaction between vegetation and hydrodynamics, and in turn flooding in fine detail, which is fundamental to the project. In addition, as it is open source, the developed model can be passed on to consultancies and partners of the project to promote further understanding of salt marshes within coastal management. Delft 3D is made up of a number of modules to solve different processes. Within Delft 3D, the different modules take input for vegetation separately. In Delft 3D Flow, which utilises the unsteadily shallow water equations in two depth average dimensions, the vegetation is described by a rigid 3D vegetation model, which takes the plant geometry as input to calculate the vegetation effect on the momentum and turbulence equations. In Delft 3D Wave, which simulates wave generation, propagation and dissipation, including the effects of refraction, shoaling and blocking in wave propagation, as well as capturing wave current interactions, the rigid cylinder approach of Dalrymple is utilised. Energy losses are calculated as actual work carried out by the vegetation due to plant-induced forces acting on the fluid. As you can see in the figure on the left, a number of different vegetation species are present within the TAF estuary. However, due to limitations in Delft 3D, it was not possible to implement different vegetation characteristics within both the flow and wave modules at the time. As such, the vegetation input was based on the characteristics of the dominant species, Atriplex portulacoides. This is input within the model in terms of the average height, stem diameter, number of stems, and the drag coefficient across the estuary. To study the impact of salt marsh management interventions on coastal flooding, a series of storms were created by combining different boundary conditions. To provide storm surge, the dataset and method of Macmillan et al. Was used. They provide peak water level conditions for a range of return periods at 2 km resolution around the UK coastline. As part of this dataset, they also provide representative scaled surge profiles based on analysis of tide gauge data around the UK, in order to scale up water level curves to the desired peak water level, incorporating the time-varying surge component. This provides a range of representative storm water level profiles for the desired significant storms. Alongside the surge, the storm wind and wave conditions were analysed. Wave data was provided from the CFAS Wave Hindcast dataset that provides wave data at 20 km resolution around the UK waters from 1979 until present. Wind data came from the Pembrey Weather Observation Station, which is in close proximity to the case study site in Carmarthen Bay. Generalised Pareto distribution was fit to both datasets to provide the required range of extreme value conditions. To create a time-varying profile through the storm event, a 3-point spline was used in combination with each of the peak storm values. 3 different salt marsh management interventions were implemented within Delft 3D to compare with the current situation for the TAF Estuary. These interventions represent a range of approaches. The first intervention was to create a hard defence at the boundary of the village of Larne, which would completely eliminate flooding. Although this idea has received strong resistance from the local residents, who want to preserve the character of the village, it is still being considered by coastal management. This was implemented within Delft 3D as a thin dam along the edge of the marsh. The second intervention is managed realignment. This approach has become increasingly widespread with UK coastal managers in recent years, who recognise the need to find alternative approaches to the construction of costly hard defences in the face of sea level rise. In this approach, areas of land are left undefended for the sea to reclaim, in order to alleviate pressures on nearby areas. Here, 2 potential areas were identified. The 2 farm sites are historic reclaimed salt marsh sites and thus provide good potential for the creation of new salt marsh. Following standard practice, the sites are breached to allow the inflow of water, with the breach width defined in relation to the increase in tidal prism that each site provides. Vegetation input is also added to each of these areas, representing the future situation where salt marsh is established within the site. As previously mentioned, grazing of salt marshes by local livestock is a common phenomenon in most Welsh estuaries, reducing the height of salt marsh vegetation. While this can have potential benefits for biodiversity, it will reduce the vegetation height and subsequently the resistance to wave and flow propagation on the marsh, diminishing their coastal defence function. To investigate the wider impact of salt marsh grazing in the TAF Estuary, the extreme case in which all salt marsh areas are grazed was investigated. Grazing was introduced into the model by artificially removing the vegetation cover from the marshes, which replicates the extreme scenario. Following model validation against measurements within the estuary, a series of significant storm events were run for each of the salt marsh management interventions. Here, the peak storm water levels are compared for the 1 in 50-year storm event. In Figure A, the peak water levels under the current condition are displayed. The tidal extent during the peak of the storm reaches the landward edges of the marshes, with water depths in the range of 1 to 2 metres. With the introduction of a hard coastal defence to protect the village of Larne, shown in Figure B, there is no significant change in the peak storm water level of the estuary. Behind the structure there is no water, as expected, but beyond this there are no noticeable changes. The change in water level due to marsh grazing, shown in Figure C, is almost insignificant. While obviously the water level difference between undisturbed and managed realignment sites, shown in Figure D, is large, there is no noticeable water level difference seen outside of the marsh areas of the estuary. In this slide, the peak storm wave heights are compared for the 1 in 50-year storm event. In the current condition, the largest wave heights are seen in the areas around the mouth of the estuary and range between 1.2 and 1.4 metres. At the edges of the marshes, close to the tidal channel location, wave heights reach 0.6 to 0.7 metres, while those on the marshes reduce to less than 0.2 metres. The hard defence at the landward edge of Larne Marsh causes very small changes in wave height, coincident with the channel at the seaward boundary of the marsh. With the reduction in wave attenuation due to the lack of vegetation as a result of grazing, the wave heights within the estuary are increased with a maximum of 0.1 metres at some locations. As with grazing, managed realignment causes a general increase in wave height throughout the estuary. These increases may be significant in terms of flooding and marsh erosion. Here, the peak flood extent is shown for the current scenario. Due to the topography of the village of Larne, the flooding does not affect the north of the village, which rises uphill. However, a number of domestic and business properties are flooded. With the introduction of the hard defences, as we've seen with the water level, there is no flooding of the village itself, as expected. While for the grazed case there is a slight increase in the extent of flooding, the actual difference in the village of Larne is very small, so there's no significant difference between that and the current condition. For the managed realignment case, there is a similar extent of flooding to the current and grazed cases for the village of Larne. The most noticeable difference you'll see here is the difference in flooding of agricultural land beyond the managed realignment site to the bottom of this figure. In conclusion, we found that for the TAF estuary, changes in salt marsh management did not significantly change the level of coastal flooding, although despite its lack of popularity with local residents, the most significant change in flooding occurred with the introduction of the hard defence. While the grazed and managed realignment cases did not significantly alter the level of flooding, they had noticeable impacts on estuarine hydrodynamics, which may in turn have impact on the longer-term management of the estuary. Finally, it's also important to note that there is large context dependency in the impact of salt marsh management interventions due to the diverse nature of sites around Wales and the UK. Thank you for listening.